Welcome back. In today's problem, we're going to use nodal analysis to determine the voltage at terminal VA, terminal VB, and terminal VC. In the circuit, we see that we have one, two, three voltage source. And when using nodal analysis, we like to see voltage sources. Current sources, not a problem, because basically what we're doing, if we take the difference between VA and VB divided by the total resistance in that branch, all we're finding is the current flowing in that branch. So if we're applying KCL at terminal VB, we wouldn't take terminal VB with reference to ground, which is 0 volts all over 7.5 ohms, because basically what that is saying is that the current in the branch is already known, which is 3 amp. So if we should say VA with reference to ground, that is 0 volts all over 7.5 ohms, that's basically telling us the current in the branch, which is 3 amperes. So let's apply KCL at each terminal. So let's start with terminal VA. So starting with terminal VA, at terminal VA, we take terminal VA with reference to the 50 volt source. We're seeing a positive terminal from VA, so that's minus a positive. So that's minus 50 volts all over the total resistance in that branch, which is 5 ohms, plus VA with reference to VB, and that will be VA with reference to VB, and that is all over 2.5 ohms, plus VA with reference to VC, that is the top branch of the circuit, and the total resistance in that branch is 15 ohms, and that is equal to 0. At terminal VB, apply KCL at that terminal VB. So terminal VB with reference to VA, so that's VB minus VA, and that is all over 2.5 ohms. We see that now if we should say VB with reference to ground, well, we don't need that, because as we said earlier, we just need the current, and if we know the current in the branch, we don't have to apply KCL at VB with reference to ground. So that's 3 amperes leaving the terminal, so that's a positive 3, plus now VB with reference to VC. So we could call that a supernode if you want to, but in this case, VB with reference to VC, so that's VB minus VC, and from VB we're seeing the positive terminal of the voltage source, so that's minus 10 volts. So the voltage across the branch minus that voltage within the branch divided by the total resistor of that branch, total resistance. So VB minus, or we could just put the 10 volts in the middle, VB minus 10 volts minus VC, and that's all over 10 ohms, and that is equal to 0. We go to terminal VC. At terminal VC, we take VC with reference to VA. So at terminal VC, we take reference with VA, so that is VC minus VA all over 15 ohms. Plus, now we do the same thing with VC with reference to VB. We're just doing it in reverse. So VC with reference to VB, and let's put the voltage in the middle as well. So in this case, from VC, we're seeing a negative terminal. So VC minus a negative is positive. So VC plus 10 volts minus VB. And that's all over 10 ohms. Plus VC with reference to the voltage source under it, which is the 2.25 volts. So from VC, we're seeing a negative terminal. There's nothing causing a voltage drop between VC and the voltage source. So the voltage, so VC, not the voltage, so VC minus a negative is a positive. So that's positive 25 volts. And that's all over 5. All over 5. And that is equal to 0. Simplifying the expression, we could find a common denominator, or we can factor out first. Factor out VA, add the constants together. You know, just manipulation. It's just a little bit of algebra gymnastic. And solution leads to VA equals to 20 volts. VB is equal to 10 volts. And VC is equal to negative 10 volts. And that's it. See you in the next problem. Bye.